Today we shall start off with the electric dipole, and once we do electric dipole, we'll start with electric fields. So I defined electric dipole last time. I said electric dipole is just two small charges separated, or two charges separated by a small distance. So the charges are equal and opposite. They are separated by a very short distance between them. And so we can find the electric field at a certain point in space due to the electric dipole. I'll start off by doing it in a general form, and then we shall then make it into a dipole. So let's consider the two charges Q1 and Q2 below. So we have Q1, and this will be Q2. Q2 will be a negative charge. We can put those two charges on a line like that. Then we can say the electric field at a certain point in space between those two can be found. So let's say this is the distance from here to here. So this is E1, is the electric field due to 1. So this is a certain point P in space. And E2 can be found. Since this is a negative charge, we shall say E2 is this electric field here. And we shall say this charge makes an angle phi here. This makes an angle theta. This distance we call R1. This distance will be R2. And let's make the distance here from here to here will be A. And from here to here, let's call it B. So based upon this, from our definition of electric field, the electric field 1 is equal to Coulomb's constant K, Q1 with a magnitude over R1 squared, and E2 is equal to K, Q2 divided by R2 squared. And we can say that R1 is equal to square root of A squared plus Y squared, where this distance, the vertical distance, is Y. So we can say this is A squared plus Y squared, and R2 is the square root of B squared plus Y squared. So this gives us our two electric fields. So now let's look at the point P itself. This is the point P. So there's an electric field here, E1, and the electric field E2. This makes an angle phi, and the other angle is theta. So this angle is phi, and that angle is theta. So we can take the components of the electric field along the x and the y axis. So we can think of this as a y axis, and this is the x axis. Okay, so we can say E1x is equal to E1 cosine phi, and E1y is equal to E1 sine phi. Okay, so just taking the components along the x and the y axis. And then the same way we can have E2x equals E2 cosine theta, and E2y is equal to minus E2 sine theta. So we can say the net electric field in the x direction, E subscript nx, can be written as E1x plus E2x. So this can be written as E1 cosine phi plus E2 cosine theta. And the En in the y direction is E1y plus E2y. Remember, E2 is negative. So we can say this is going to be E1y is E1 sine phi. The negative is up here. You see that E2, because it's pointing downwards in the y direction, there's a vector down, so it's negative. So E2y is minus E2 sine theta. So we can put them together. We can say the E and x. So E and total in the x direction is going to be E1, which is K Q1 over A squared plus Y squared cosine phi plus E2 is K Q2 divided by B squared plus Y squared cosine theta. because we've already established that R2 squared is B squared plus Y squared. So when we use E2, that's what we shall have. And then for the Y component, E and Y, Q1, which is E1, which is K, Q1 over A squared plus Y squared, and this is sine phi minus K Q2 divided by B squared plus Y squared sine theta. So we've got the X component of the electric field, the total X component, and we've got a total Y component also. And we can say that by symmetry, we can say that, let's do it this way. Let me start off this way. So that formula is a general formula for an electric field of two charged particles separated by a small distance between them at some point P in space. If we want to consider this a dipole, then we can take some advantage of some symmetry. So if it's a dipole, we shall assume that Q1 is equal to Q2, also A equals B, and then we shall also say that theta is equal to phi. So once we make that assumption for the dipole, because for a dipole we want the charges to be equal and opposite, and we want them to be separated by a very small distance between them. And so we are saying Q1 is equal to Q2, A is equal to B, and we are taking the angles to be the same since the charges are equal. So in that case, we can now compress our formula for En in the X direction to be equal to K, and let's say Q is just a general charge. So since we're saying Q1 equals Q2, we can just say Q is a charge, and divide that by A squared plus Y squared, and then let's use theta, so we have cosine theta plus K Q over A squared plus Y squared cosine theta. So this gives us 2KQ divided by A squared plus Y squared cosine theta. That would be the electric field along the x-axis. And then we can say that by symmetry, the electric field in the y direction is equal to 0, and we can see why that is true. So En y is equal to K Q over A squared plus, Y squared. Remember, we've already said that this is going to A is equal to B, so we have A squared plus Y squared, and this is sine theta minus K Q over A squared plus Y squared sine theta. So this is equal to 0. So by symmetry, the Y component of the electric fields will cancel out. So the electric field for the dipole is given by the X component, which is just going to be equal to 2KQ over A squared plus Y squared cosine theta, where we can say that cosine theta is equal to, from this geometry here, cosine theta would then be equal to A over cosine theta is adjacent over hypotenuse, so A over R2. A over R2. So cosine theta is equal to A over R2, which is just equal to A over R, which is A over R, A over the square root of A squared plus Y squared. So R is equal to A squared plus Y squared half. Therefore, we can say cosine theta is equal to A over A squared plus Y squared raised to the power half. So if we use that, then we can say the electric field from the dipole is given by 2KQ divided by A squared plus Y squared multiplied by A divided by A squared plus Y squared half. So we shall have 2KQ, and that will be A divided by A squared plus Y squared raised to the power 3 over 2. Any questions at this point? So from here we can do some analysis. We can say that since we are saying that this is a dipole, we can say that the distance y is much larger than a. Okay, so we are saying the dipole is two small charges separated by two charges of equal and opposite magnitude separated by a very small distance, say a. So if we take the electric field at some distance very far away from the dipole, then we can say y is much greater than a. So we can say E n for the dipole is going to be 2k q times a, and we're just going to have y cubed at the bottom. Because y is much greater than a, the denominator becomes just y squared raised to the power 3 over 2, which is just y cubed. And so the dipole can be written as 2k qa over y cubed, where we know that the charge times the distance is the dipole moment. So we can say 2k times a certain dipole moment p divided by y cubed. Okay, and I'll say that where p is equal to q times a, and this is the dipole moment. So this is the field of a dipole at some distance from the dipole.